Unit 9, Dimensioning Welding Prints. In previous units, objects were described by their shape. Shape description gives an understanding of the proportions of the part, but it does not give enough information to build a part. Dimensions are numerical values describing the size, location, geometric characteristics, or surface texture of a part or its features. Figure 9.1 shows a large weldment held in a fixture. Imagine the fit-up difficulty if the print dimensions were incorrectly interpreted. The types of prints and production methods generally determine which dimensions are found on the prints. The dimensions for a machining print may be different than those used for an assembly print. Likewise, the dimensions given on a welding print may be different than those given on a formatting print. Extension and dimension lines. Several dimensioning systems have been developed. The most common is the traditional extension dimension line system. Figure 9.2 shows a print of a simple butt joint. The top view shows the length of the part or the overall dimension. A feature dimension is used to indicate the length of one of the plates used for the joint. Feature dimensions are used to show individual features, such as the center of the hole or the location of individual parts welded into the assembly. Notice the dimension for the length of other individual plates is not shown. Only the dimensions required to accurately describe the part are given on the print. Dimensions are not duplicated. If the overall length of the part is given in the top view, for example, it is not repeated in the front view. Usually the overall length dimension is shown in the front or top view. The overall width is shown in the top or side view. The overall height is shown in the front or the side view. See figures 9.3. Sometimes the length in dimensions is called the width. The width dimension is called the depth, and the height dimension is called thickness. Dimensions can be given as linear or angular. Customary English units of measurements may be used, or metric dimensions may be given. For the customary English system, fractional inches and decimal inches are most common. The millimeter is most common unit of metric dimensions. Dimensions are usually read from the bottom of the print. The method of dimension placement is called unidirectional dimensioning. Today, most CAD drawing prints use this method of dimension placement. However, older manual drawn and reproduced prints may have aligned dimensions, so the horizontal dimensions are read from the bottom of the print and the vertical dimensions are read from the right side of the print. The extension and dimension line method includes the traditional method of an overall dimension located furthest out from the view and broken chain dimensions, or chain dimensioning. The chain dimension method does not include an overall dimension, and the accumulation of tolerances for each feature often exceeds the tolerance of the overall dimension. When using the broken chain dimensioning method, the undimensioned feature accumulates the tolerance. More information about tolerance is given later on in the unit. An angled dimension line is an arc drawn through the center of the angle at its apex, or the uppermost point. Angles are dimensioned using degrees. For greater precision, they are dimensioned in parts of a degree. Parts of a degree may be shown as minutes and seconds or dimensional degrees. There are 60 minutes to 1 degree and 60 seconds to 1 minute. Angle dimension examples are shown in figure 9.6. Datum dimensions. When a single side of a part is used to start all of the dimensioning method is referred to as datum, or baseline dimensioning. A datum or baseline is a starting plane or edge. Notice that when laying out a part, the datum dimensioning system minimizes the compounding of an error. Referred to figure 9.7b, if there is a plus minus 16 error in layout or each of the dimensions given in the chain, then the overall error of the part would be 3/16. Zero plane dimensions. Zero plane dimensioning uses a single plane, usually the edge of the part or intersecting planes, as datums from which dimensions are derived. The zero plane dimensioning system does not use dimension lines. Instead, its feature is dimension from a zero plane indicated by an extension line ending with a box. The box holds a number that indicates the zero plane number. Dimensions are shown at the end of the extension lines linked to the specific feature requiring a dimension. This method minimizes the chances of introducing error into the part layout and reduces the amount of room needed on the print to contain the dimensions. Figure 9-9 shows a print using the zero plane dimensioning system. Notice the vertical dimensions are read from zero plane 0, 1 and horizontal dimensions are read from zero plane 0, 2. Be careful to determine whether the zero plane or where the zero plane is located. Sometimes a feature is used for locating the zero plane rather than the edge of the part. Figure 9-10 shows the center of the hole as the location of the zero planes. Direct and calculated dimensions. It is important for a detailer to think like a welder, machinist, fabricator when detailing a drawing. Sometimes the designer does not consider or know the order in which the processes used to build a part should be completed. Most dimensions given to features used to build the part should be direct dimensions. Figure 9-11 or 9-11 shows dimensions to the edge of the two vertical plates welded to a base plate. However, to minimize error in the layout of the vertical plates, both vertical plates should be laid out from a single edge. A calculated dimension is required to determine the distance from the left edge to the second vertical plate from the right. Notice the distancing to the left edge and the right vertical plate is 2 inches. Example, in figure 9-12, the center-to-center dimension on the holes shown in the top view is missing. Assembly for this part may rely on the accuracy of the center-to-center dimension. Therefore, a center-to-center dimension needs to be calculated. In figure 9-12, calculate the center-to-center distance by adding the center-to-end distance for both holes and subtracting from the overall dimension. The center-to-center dimension is now 4 inches. Linear and angular tolerance. Tolerance is the total permitted amount in distance or degrees. An exact or basic dimension may vary. Because there are some variations in all manufactured products as a result of the processes and measurement systems, all parts will vary somewhat from the print dimensions. A permissible variation must be determined so the function of the part will not be affected. Total variation in a part comes from both the manufacturing processes and the measurement system. This is why measurement instruments should be checked against a standard and equipment should be maintained. Tolerances on a print may be given as a general tolerance or as an explicit tolerance. The general tolerance is usually found in the tolerance box in the title block or in a note. Figure 9-13 shows the tolerance in the title block. Notice the number of X's represents the number of decimal places in which the tolerance applies. That is, .xx indicates a dimension with 2 decimal places and .xxx indicates a dimension with 3 decimal places. Figure 9-14 shows an example of an explicit tolerance with a maximum and a minimum limits listed. Tolerance may be given as a fraction, dimensional, decimal fraction, metric value, or in degrees. Tolerance may also be unilateral or one-sided or bilateral, two-sided. In figure 9.15, a bilateral tolerance is shown. Notice the length of the part may vary to maximum length of 2.56 inches or a minimum length of 2.44 inches. The maximum distances are called limits. Figure 9-16 shows a unilateral tolerance. The location of the part may only be more than the print dimension, not less. Reference dimensions. A reference dimension is used for information of convenience only. No tolerances apply to a reference dimension. Figure 9-17 shows the use of a reference dimension. Notice the reference dimension is between parentheses. The other method of including a reference dimension on a print is by using the letters ref after the dimension. Geometric dimensioning and tolerancing. There are occasions when linear tolerances do not provide the best method of showing the correct relationship between parts or features of a part. A designer uses geometric dimensioning and tolerancing to specify the requirements of a part by the actual function and relationship of the features. Consider the drawing in figure 9-18. The support bracket shows two parts in a welded assembly. The vertical part has 4 machine holes at the location shown. The welding symbol indicates a one side or arrow side only fillet weld. For this weldment, the designer has specified a linear tolerance of plus or minus 0.062 inches. When welded, it is likely the fillet weld will shrink and the vertical part will warp and move. When inspected, the position of the bottom of the vertical part is within tolerance. But look at the top of the vertical part after the weld is complete. As shown in figure 9-19, the top of the part has moved, so the holes will not be in position required by the mating part. The welder can measure the position of the bottom of the vertical part and verify the part is within tolerance. As the part moves to assembly, the part will be difficult or impossible to assemble. The part may require rework or remove the warp, or it might be scrapped altogether. Definition and symbols. Geometric dimensioning and tolerancing symbols are used to indicate the relationships between parts and features. Although the concepts of the GD&T are often complicated and confusing, when used in welding and fabricating, you will only need to know how to apply a few of the symbols. Earlier in the unit, the datum was introduced for dimensioning purposes. In GD&T, the datum is defined as an exact point, axis, or plane from which the location or geometric features of a part are located. The datum identification symbol is shown in figure 9-20. The symbol is relatively new to industry, and many prints still have the older datum symbol shown in figure 9-21. A feature is often used to describe a physical portion of a part, such as surface, hole, or edge. Sometimes a feature is used to establish a datum. When an actual feature is used as a datum, it is referred to as a datum feature. Figure 9-22 shows the symbols used to specify tolerances and geometric dimensioning. The symbols are grouped into 5 types of characteristics linked to individual features or to other features. The types include form, profile, orientation, runout, and location. For welded parts, orientation and form are the most important, although some other types may be used. Application of GD&T. The application of GD&T starts with the identification of the datum. Generally, datums are identified by the datum identification symbol and lettered in order of importance, starting with the letter A. If the part is a rectangular solid, the datum references are established as the 3 mutual perpendicular planes shown in figure 9-23. The primary datum reference is listed first, and the secondary datum reference, and then finally the tertiary datum reference is shown. Once the datum reference is established and a feature or group of features is linked to the datum by a feature control frame, figure 9-224. This frame shows the perpendicular symbol and the diameter symbol to establish the tolerance zone and the material condition symbol and the datum reference. For a welded part, the feature control frame might look like figure 9-25. The feature control frame shows the perpendicular symbol, the tolerance, and the datum reference. If feature control is red, the feature must be perpendicular within 0.125 inches with respect to datum A. Notice the tolerance shown on 0.125 inch wide in which the controlled feature is included. Therefore, the feature may be warped, misaligned, or twisted, but the plane established by the edges of the part must not break the tolerance zone. Orientation geometric tolerances. Orientation geometric tolerances control the degree of parallelism, perpendicularity, and or angularity of the feature with respect to one or more datums. Figure 9-26 shows the orientation geometric symbols. Figure 9-27 shows a part with two parallel vertical plates welded to a horizontal plate. The left plate is used to establish a datum from which the right plate is only permitted to vary within a tolerance zone of 0.062 inches. Formed geometric tolerances. Formed geometric tolerances are used to control flatness, straightness, circularity or roundness, and cylindericity. The tolerance controls the feature and is not linked to a datum. Figure 9-28 shows the formed geometric symbols. The symbol shown in the feature control frame in figure 9-29 indicates straightness. The plate surface controlled by the feature control frame is required to be within 0.005 tolerance zone. Datum targets are used to establish consistent locations on parts with rough or irregular surfaces. The datum target is usually circular and indicates where the part should contact the fixture. The use of datum targets helps assure the proper location of parts in a fixture. Figure 9-30 shows a datum target symbol. When the datum target is visible on the view, the target appears as shown on figure 9-30. Hidden targets have hidden lines in the top half of the target. The hidden datum target is shown in figure 9-31. The targets are usually lettered, starting with the primary target lettered X. Other geometric tolerances for welding, the orientation and form geometric tolerances are the most important. Although other types of geometric characteristics may be indicated on a print, some of them may be important depending on the shape of or geometry of the part being welded. Positional or location tolerance are used to establish the location of features. In figure 9-32, a positional tolerance is used to control the center of a hole with respect to datum A, B, and C. The positional tolerance provides a tolerance zone based upon the shape of the feature controlled. For the hole, the center may vary within the circular tolerance zone with a diameter of 0.004 inches. Runout tolerances controls the variation of the straightness, circularity, cylindericity, or angularity of surfaces with respect to the center line or axis of the cylindrical parts. If two cylindrical parts, like two parts of a shaft, are welded together, The runout tolerances control the straightness of the shaft. Figure 9-33 shows a welded shaft indicated a total runout tolerance of 0.003. Figure 9-34 shows the application of the runout tolerance and the inspection method to check the runout.